Hello. Let me see if this is working. Okay, it is. Okay. Um, Basically, this is gonna be for my chemistry test. I'm gonna start making absolutely no sense. So yeah, that's what's going on. Um, oh, I don't have a lot of time to talk about this. Okay. Um, Actually, no, I have an hour. I have an hour. I don't know what I was talking about. Anyways, I just need to be quick. Okay. So basically, we're talking about three things: IR, MS, and NMR. IR is basically infrared spectroscopy, and it tells you the compound structure based on vibrating bonds. And the x-axis is the wave number, the y-axis is transmittance. So you draw a line at 1500 to differentiate the fingerprint region and the sp3 carbons, and then another one at 3000 to differentiate that sp3 area from SP and SP2. So little notes. So from 0 to 1500, that's basically the unimportant fingerprint region. Then you got 1500 to 2000. You got double bonds here, a lot of double bonds at least. So CO, CC, and then aromatics and benzene. And then you go all the way to 200 to 3000, or 2000 to 3000. You got sp3 CH, and then aldehyde CH, and then you also have triple bonds to C and N. And then above 3000, you have bonds to hydrogen like OH, CH, and NH, and then you got sp and sp2 CH bonds. You got a whole bunch of distinguishing features. So if you have um like a C double bonded to O, and then you have two additional waves, like a jagged wave at 2900, and then another one at 2700. That's an aldehyde, because a ketone only has a smooth big wave at 2900. Um, and then if you have a primary amine, which is NH2, connected to one thing, it has a double peak, and then a secondary amine that is connected to two things, which is also NH2, that is going to be a single peak. sp3 alkanes are going to be at 2900 to 3000. 3000 to 3100, that's going to be alkene sp2cs. And then 3000 and up, that's kind of like where the alkynes are. A lot of broad stretches are taking up the whole chart pretty much. If like a lot of times you see like a broad stretch of things, that's probably carboxylic acid. Because it has both a bond to an oxygen, a double bond to oxygen, and a OH. So lots of functional groups to be discovered. Okay, that's all you need to know pretty much for IR. Now you're moving on to mass spectrometry. That basically tells molecular formula based on the exact mass. The x-axis is the mass to charge ratio, and then the y-axis is the relative abundance. The base peak is going to be that tallest peak, so it's going to indicate the most stable cation. So it's going to split the molecule into like different kind of types of molecules, and so like the most abundant is going to be the tallest because it measures abundance of all these cations. So the parent peak is the first peak of the farthest right cluster, because as you move down, it measures the mass. So if the right cluster is going to be the most mass, and so if you look at the first peak of the farthest right cluster, it's that's the parent peak or the M plus peak, and usually, but not always, it is the base peak as well. Anyways, it indicates the exact mass of the molecule and is the most common isotope. It can also indicate the presence of nitrogen, because if M over Z is odd for the base peak, or like the parent peak, then like that's 100% like presence of nitrogen. Like You don't really need to know much else. Like you already know that's an odd number of nitrogen. Otherwise, it could be even or 0. The M plus peak is the peak to the right of the um, M plus peak. This indicates the number of carbons that you have, because basically the abundance of M plus 1 over the abundance of M plus, you divide that by 1.1 multiplied by 100, and then you get the number of carbons that you should get. The max number of hydrogens or halides in a molecule is determined by 2C plus N plus 2. And then the N plus 2 peak helps indicate the presence or absence of Cl or Br. So if the M plus to N plus 2 ratio of abundance is 1 to 1, then that's Br. And then if it's a 3 to 1 ratio, then it is the presence of Cl. Degrees of unsaturation helps determine pi bonds and structures. So the formula is 2C plus N plus 2 minus halogens minus hydrogens divided by 2. So for example, I'm not going to give an example. Du indicates pi bonds and rings. So 1 du is 1 pi bond. 2 du is either two pi bonds or 1 triple bond. And then 4 du is generally, like, usually it indicates that there is a ring. Or there could just be a lot of like pi bonds. Additional tips. So like the most common isotopes are used for MS. So like for carbon, it's C13, it's H1, 016, N14, Br79, Cl35. So those are the most like common isotopes for those elements. So like when you're subtracting like these mass units, because you're trying to determine like what the molecular formula is, so you have like a total number of mass. When you're subtracting these mass units from like the total mass, make sure you're like subtracting like, for example, like 79 AMU from Br, not 79.9, because you're not doing the exact mass, you're doing the exact mass of the most common isotope. Okay. And so if oh yeah, and then the M plus 1 or the M minus 1 indicates the loss of a proton. And then if your molecule has lost an alcohol group, the M plus peak will be at M minus H2O or M minus OH. So you would need to add or subtract the mass of either H2O or OH, respectively, to get the M plus if it's lost water. After determining all the atoms, you can find the number of hydrogen by subtracting the AMU of carbons and heteroatoms from the total AMU. Basically, you you get that M plus like mass, right? And then you subtract the mass of all the heteroatoms, and then you subtract like the number of C's multiplied by 12, because that's what carbon is, I guess. Wait, I would think it's 13, not, yeah, I think it's 13. You multiply it by 13, not 12. Okay, now we're moving on to NMR, which is the last thing. It's nuclear magnetic resonance. It tells you the compound arrangement based on nuclear spin. This is easier when nucleus is shielded by electrons, because the opposite magnetic force exerted by the electrons will shield the nucleus from feeling the full applied force, which means a low wave number. So 13C NMR is pretty common. You use a concentrated sample and you run it for a longer time. 1 NMR. So that's when you use like a deuterated solvent like CdCl3. Others are like C6H6, D2O, or CD3N. Those are all like deuterated solvents to identify the H, basically. So CNMR, there's two characteristics. First is chemical shift. This is a frequency absorbed by your nucleus. So downfield would be from a deshielded nucleus. And this is where all the more electronegative atoms or sp2 carbons, like double bonds and aromatic rings, are. Upfield is a shielded nucleus. So this is where the sp3 and sp carbons are at a lower number. And then equivalence. So the second thing, is equivalence. So like equivalent carbons will emit the same signals, basically the same electron environment around each of these carbons. So if a line of symmetry can be drawn, only one side has distinct signals. If two are drawn, only count one side. For example, benzene has six signals one signals because all six carbons are equivalent and it's symmetrical on all planes. Double bonds do not have free rotation, so the H's may not be equivalent, and then single bonds have free rotation, which allows for equivalency. So all H3s connected to the same C are always equivalent, and then H2s are equivalent if there are no chiral centers. So you have to memorize this, but basically it's the depth thing. So the distortionless enhancement of polarization transfer. So CNMR shows everything, especially just like singular C's, like the distinguishing feature is just normal, like C with no H bonded. So CNMR shows CH3, CH2, CH, and C, and it's a positive signal. DEP90 only shows CH, like it only shows CH as a positive signal. And then DEP135, it shows CH3 and CH as a positive signal, but the distinguishing feature is the CH2 is negative. Okay, so for HNMR, there's four key characteristics for this. So there's equivalence. So equivalent hydrogens have the same signal. They have to be on the same carbon plus the same environment. And then you watch for non-equivalence. So basically, geminal protons on an alkene can be non-equivalent due to halogen, or resonance. Non-equivalent protons on a cyclopropane or cyclobutane are more detectable than cyclohexane. So cyclohexane might like appear as equivalent, and it's like actually not. And then peak location compared to a reference. Oh wait, sorry. This is chemical shift. This is where the signal is compared to a reference. So like this HNMR, it's gonna have like a solvent peak, like TMS or CDCl3. So like basically, um, CDCl3 has a peak at 7.26 parts per million, and then TMS has a peak at 0. So you kind of ignore those, but you like kind of count where it is shifted from that location. So a more deshielded atom will be more downfield. So anyways, pi bonds will produce diamagnetic anisotropy, which basically extra deshields alkenyl and vinyl protons and outside aromatic protons. But this anisotropy also extra shields the alkynyl protons and inside aromatic protons because they're trapped in the pi bonds. So basically, deshield the alkenes and outside, and then shield the inside. Integration basically means each peak is labeled with a number of hydrogens it represents. That's pretty much it. Splitting is when a proton signal can be interrupted by nearby bonds, or like nearby unequivalent protons, 2 or 3 bonds apart. A normal signal is a singlet. If basically you count how many non-equivalent neighbors, proton neighbors, hydrogen has within 2 or 3 bond distance, and then that number will be n, and then you do n plus 1. So if n plus 1 is so if n is 0, then you have n plus 1, so that's 1. So you have 1 peak, and that's a singlet. Then if it's 1, then you do 1 plus 1, that's a doublet, triplet, quartet, quintet, sextet, septet, octet, nonet, and then multiplet. OH and NH can appear as a broad semicircle singlet, and if this proton signal disappears with a D2O test, which is you just add D2O, OH or NH might be present. The deuterium test is used to determine if two hydrogens are equivalent or not. So you do this by drawing two compounds. So you draw one with the H in one position and D at the other, and then the second one you kind of switch the H and the D. This is to figure out if they're the same compound or not. So homeotopic means they're the same exact compound, and aneotopic means um, the carbon is chiral after the deuterium test, and is the only chiral center. So like it's they're kind of like two mirror compounds that reflect on each other if you draw a mirror plane. Um, and like the H dot equivalent. Diastereotopic is there's more than one chiral center in the molecule after the deuterium test, and the H's are not equivalent. Um, and then coupled with protons, basically protons that split each other, split with the same coupling constant called J. And I'm gonna look here just to see. Okay, so basically, if you get a question that says like, does that decide the structure of the compound on like basically HNMR spectrum and molecular formula. So if you're given the molecular formula, first thing you're gonna do is the DU. It'll give you um basically your DU and then your proton signal. Um, you find like the biggest proton signal. Um, and based on basically what that is, you kind of know the structure. So you analyze each signal at like each thing, like each of the HNMR. So um, you'll have that chemical shift, like I said. So the chemical shift, for example, like if you have a chemical shift at 1.2, 2.87, 7.1, there should be a chart. So basically, like you'll see that like it's basically a ring, and then like you analyze the signal at 2.87 and so on. And it'll give you like a parentheses. It'll say like a letter and then like a number and then H. So that letter is gonna be like it'll tell you if it's like a multiplet or like a singlet or something. Like it basically tells you the um like the splittings patterns, and then the number basically indicates the number of hydrogens that you have. So yeah. In this example, it says it's monosubstituted. I don't know how, but I think it's from the chart. H chart of functional groups. 7.1 or whatever it was. Okay, so well, it's basically a monosubstituted aromatic. So yeah. So you just basically analyze all of them, and then you try to put them all together. Like you find the little section, and you add them all together. Okay, another thing is like if like basically the letter that goes before, like for example, D comma 3H, so that D will let you know that like whatever like the environment is around that specific carbon. So for example, like it's a D, so it's a doublet, so you know that like it has n minus one neighbors. So basically n or not n minus one, but like the peak minus one neighbors. So for example, like the doublet is a number two. So you have to do n plus one to get there. So you do that peak minus one. So that's one. Which means you have one neighbor, if that makes sense. So for example, if it's like a sextet, you know you have five non-equivalent neighbors. If you're asked to propose a reasonable structure for the unknown chemical based on the HNMR spectrum, you look at the signals where they are. So if it's like, for example, super far down at 12 or something, and it's like one signal or like one hydrogen, then it's probably like R double bonded to O, double bonded to OH. I think carboxylic acid maybe. Um. So yeah. So that one was at 12 parts per million. The one at 2, you look at the integration splitting. Um, so basically, the chemical shift tells you what functional group it is. Integration tells you how many. Same thing. It also tells you how many functional groups there are, but like, it just tells you how many hydrogens are involved. And splitting lets you know like how many, like where it's near, like what it's near. If you're given a molecular formula, make sure you like the first thing you do pretty much is calculate the du. Um, Another thing, the equivalence data that you're getting, make sure that like if you have a lot, like the less signals you have, the more equivalent your protons are. Or yeah. So like just make sure that like if it's less like signals, it's probably like the aromatic ring might like, let's say you have a dye substituted aromatic ring, like you might like have complete symmetry with that, with the top and bottom, like if it's para substituted, um and so just look at the equivalence like numbers and whatnot, to see and check and make sure. Because they could be like on a different position, not always on opposite ends, not in the para. Let me check. So okay, if they're right next to each other on a hydro carbon ring is ortho, then the next position is meta, and then the position right after that, which is opposite, is para. This question gives you it gives you a total AMU of m plus. It gives you the m plus to m plus 1 ratio, and it gives you that um, IR spectrum. So basically, first what you do is you calculate the number of C's based off of that ratio that you were given. So it'll be n plus 1 over n plus. And then you divide all that by 1.1, and then you multiply all that by 100%. Get the number of carbons. And then from that IR, you can figure out all the heteroatoms or whatever. And then you subtract all the heteroatoms and the carbons from the one like basically the total AMU. So like you subtract the masses and whatnot, and then you should get the amount of hydrogens, and then you get the molecular formula. You can calculate the DU. Um, Let me see here. By the way, again, if you see like a signal at like 79-ish, ignore it. It's CDCL. And if it's at 0, then it's TMS. And then after that, you just match the H values to the H NMR, and then you match the C values to the C NMR. And then I guess just like another reminder that dang, I really missed that. Another reminder if you see a lot of okay, if you see a lot of like for aromatic ring, especially if you see a lot of like signals, it means that there's just no symmetry, no equivalence. I know it goes without saying, but just make sure. And then lastly, let's go here. Um, Again, the greatest chemical shift is the greatest electronegativity. Like the closer it is to an O or the more double bonded, like um like if it's the closest to O and it's the most double bonded, like double bonds are always going to be the most chemical shift. Or the close like for example, like the carbon participating in the bond um or participating with the contact with the O molecule um is the most shifted, and then the second one is the carbon that's close to that bond. And then just a like quick reminder. So like C or never mind. So like in depth 135, CH3 is positive, CH2 is negative, CH is positive. No signal for C. For depth 90, there's no signal for CH3, CH2, or C, but there is a positive signal at CH. Um, and then if they give you like a ppm list for signals, like yeah, basically just label the carbons with the most, like basically identify the carbon with the most shift. That one gets the highest signal. Um, in CNMR, the highest like peak or whatever, um, that represents the most carbons. So if you see like a whole bunch of peaks that are kind of the same height, that's probably one carbon, and the higher ones have multiple. And again, the more close to oxygen or the more double bonded, the more downfield it is, the higher wave number. If it's a alkyne close to an N, that one will be more downfield than the other part of the alkyne. If it's asking you to match like spectrums or whatever, just make sure that like you're counting how many signals you're supposed to get, and then you count how many signals are in the spectrum. It makes it a lot more easier for you. You don't have to really look at it. So if it's asking you to propose a structure for a compound with the molecular formula with a given IR carbon 13 and dep 135 and NMR, first you look at the IR, you identify the groups, then you look at the NMR, look at where the groups are just to identify where, like, if there are, like, to verify the groups, calculate the DU. Look at like the chemical shifts for the CNMR. And then you just kind of test out different structures just to match the criteria. So like make sure like the structure matches the molecular formula, matches the DU, the IR has like the IR requirements are all there, NMR requirements are all there. Like make sure like you have a certain number of sp3 carbons or a number of sp2 carbons. And like make sure the dep 135 or whatever basically like agrees with all of you. But anyways, yeah, bye.